Hello, Stat. This is the answers to the rest of the problems that you were assigned to do on Thursday night. So you'll be looking at this in class on Friday. We've covered up through number 6. I will let you gaze at the answers again between 1 and 6 in case you didn't get those. You missed one. And you can watch this video and slow it down and observe them in a better way. The last one, on number 6, we decided if a distribution is skewed right, the only thing the central limit says about the situation, about x bar, if n is large, the sampling distribution for x bar is approximately normal. So we know that large means greater than or equal to 30. Alright, so let's go ahead and finish this operation by looking at number 7 through 13. Be right with you here. Yes, number 7. Alright, so let's see if I can get it in the screen. Alright, pretty much in the screen. Alright, an SRS, I think this was supposed to be an SRS. An SRS is selected from 37,000 persons. Another SRS of the same size is selected from 4 million. How do there's the standard deviation of x bar compare? So we're looking at spread here, and the only thing that's changed is the size of the overall populations that the two were selected from. And it turns out that the spread, the standard deviation of x bar, will be the same. The size of the population does not affect spread. So since we are keeping the sample size the same, the spread, standard deviation of x bar, is the same. It came from the old corn scoop idea. The corn scoop draws a sample from a sack and is similar to drawing a corn scoop from a truckload of corn. So the size of the population does not affect anything. Alright, so the standard deviation of x bar is the same if the sample size is the same. On number 8, you were looking at chipmunks, and they had a mean of 84 grams, standard deviation of 18. Doesn't say anything about their distribution, their population distribution. They're going to have a sample with size 9, and which are true. So the first statement says x bar, the mean of x bar is 84. That is always true. And the standard deviation of x bar, well, we have to see if we can even take the standard deviation of x bar. So to check that, we do 10 n is less than big N. So 10 times n is 9. So we have 90 is less than all the population of chipmunks. So we can do x bar. We can do the standard deviation of x bar. So we recall that the standard deviation of x bar equals the standard deviation of the population divided by the square root of n. In this case, 18 over the square root of 9. 18 divided by 3 is 6. So it's not this one, but it is this one. What about the shape of x bar? So the shape of the population, well, I think they're talking about x bar. So the shape of the sampling distribution of x bar, is it normal or do we not know? Well, it wasn't stated that the original population was normal, and so we can't go from that standpoint. So the other thing is n has to be greater than or equal to 30 to approximate normal. So sometimes an n as small as 9 will work, but it all depends on the shape of the original population, which we have no idea. So we're going to just have to go with shape unknown. All right. So let's look at the next one. Interpupillary. That's the distance between your pupils. The black part in the middle of your eye is normally distributed, so I'll take a note of that. Here's the mean, the standard deviation. We select 5, so that's the size of little n. What is the probability the mean of the sample is greater than 60? So let me write that out in symbols. The probability that the mean of the sample, which is x bar, is greater than 60. All right, so there's some things I've got to check out. Can we use normal privileges? Yes, because it came from a normal population. We know x bar is also normal, no matter the sample size. So we're okay. We checked out normal. And we have to use the standard deviation to get a z-score. So let's check out, can we find the standard deviation? Is the check for that 10n less than big N? So we have 5, 10 times 5 is 50, and there's lots of faces in the world that have interpupillary distances. So 50 is way smaller than the population. So we can find the standard deviation. So over here I'll collect the data that I need. The mean of x bar, we'll need that, is the mean of the population, 62.5. And the standard deviation of x bar is always the standard deviation of the population divided by the square root of n, in this case square root of 5. So onward, let's use our normal privileges. So we're going to do a z-score. The number of interest is 60, so we're going to do 60 minus the mean, which is 62.5, divided by the standard deviation. I didn't tap that out, but it's 6 over the square root of 5. I'm sure you did. So when I did all that, I got negative 0.932. Chart A led to 0.1762. So are we going to accept that, or do we need 1 minus that? Greater than. Remember, the chart tells us less than, so we are going to do a 1 minus. All right, hopefully you did that as well. 0.8238 is so like an 82% probability of having, and that sample having the mean greater than 60. All right. All right, on number 10, 53% of all adults. So when you see a percentage, it looks like we're going into p-hat land. So p-hat team, be helpful. 53% of all the adults in Ohio supported the candidate. An SRS of 500, so that's means the little n. What is the probability that less than half, so what proportion are they talking about? 0.5, then half the sample agree. So we are going to go ahead and check some things out before we go any further. Let's check if it's normal. So it doesn't say that it started from a normal situation. We're on p-hat land, so what do we have to check? NP is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. N is 500, so we have 500 times the 0.53. I don't know what that is, but it's way greater than 10. And then here we have 500 times an even bigger percentage, not 0.65, but 0.47. I don't know where that came from. 0.47 is 1 minus p. That's way greater than 10. So I checked normal. So let me gather some things that I need. The mean of p hat, sorry, stuck in X bar land. The mean of p hat is the mean of the whole population, 0.53, and the standard deviation of p hat is going to be the square root of p, 0.53, times 1 minus p, which is 0.47, divided by n, all under the radical sign. And that is if, and 10n is less than the whole population. 10 times 500 is 5,000. Is that less than all the adults in Ohio? Yes. So we're going to check that off. And when we calculate that, we get 0.022. All right, so these are the tools to find the z-score. So what are we looking for? What is the probability that less than half the sample agrees? So we want to say p hat is less than 0.5. Remember, when we're dealing with p hat, we have to take the words and make them into a proportion, half being 0.5. All right, so let's z-score it up here. 0.5 is the number of interests minus the mean, 0.53, divided by the standard deviation, 0.022, and that led to a z-score of negative 1.34. Chart A is 0.0901. Do we stick with that, or we do 1 minus? All right, it's less than. So the chart holds true. It tells us less than, so we're going to stick with that, about 9%. All right, hopefully you got to that answer before I did on your lonesome. All right, on number 11, egg weight is normal with the mean given as 65, standard deviation 5. And what is the probability that eggs weigh between 62.5 grams and 68.75 grams? So we are looking for the probability that eggs, notice there's no sample taken here, so they're just saying eggs. So this is not a sample or a proportion. There's no statistic involved in part A. They kind of tried to slip one in on us. It's just a random variable. So we have the probability that a random variable x, being the weight of the egg, is less than x is less than 68.75. So there's nothing to check. We're just going to do it. It's just an oldie but goodie from chapter 2 or wherever we learn to do this sort of thing. You have to get a z-score for this, a z-score for that. Go to chart A and find the difference between the two values in chart A. So the z-score for this number, 68.75 minus 65 over 5, gave me a z of 0.75, and chart A led me to the number 0.7734. This number over here, z-score, it's 62.5 minus the mean over the standard deviation, gave me a number of negative 0.5. And that chart A gave me 0.3085. And you'll recall, then this gives us the number below that, this gives us the number below that. So how do we get the one in between? We subtract, and when I subtracted those two, I got 0.4649. And that's the number I accept, about 46%. All right. Now we are going to take a sample. Did you notice the sample is 1 carton of eggs, so n equals 12. So that carton is the sample. 1 carton is selected. Find the probability that the mean weight of the eggs falls between these two numbers again. So we'll see if the probability increases or decreases now that we're just drawing out one carton of eggs. So we do the same thing, except we got to find the mean and the standard deviation. First of all, we do a normal check. And it does check because it started out with a normal population, so X bar is a normal sampling distribution. So we can use normal privileges, that is chart A. Then let's start gathering our information. The mean of X bar is the mean of the population, 65, and the standard deviation of X bar is going to be the old standard deviation, 5, not old, but the one of the population, divided by the square root of the number in the sample, which is 12 eggs. That is true if 10n is less than n. So 10 times 12, 120, is that less than the number of eggs in this population? I'm assuming yes. Alright, so now 5 divided by the square root of 12 came out to 1.44. And now I'm ready to do all the z-score stuff. So I'll do this one first. 68.7 minus 65 divided by, this time, 1.44 gave me a z-score of 2.6. Chart A said 2.6 was 0.9953. Alright, without writing out the other one, I'll speak it. 62.5 minus 65 divided by 1.44 gave me a z-score of negative 1.73. And that one, the A chart, gave me can't be negative. It's 0.0416, 18. And I subtract these two, and I got 0.9535. So we had a higher probability of it happening with a sample than we did with the whole population. All right. Did you need to justify to know that the population distribution of egg weights was normal to complete Part A? On Part A, we always have to, before we can use z-scores, we have to know it's normal. So I'm going to say we do have to justify the normal condition for A and B. For A, it was that simple because they said it was normal. So that's all we had to go with. And on B, we already checked it. This sort of redundant question because we checked normal off, even though it was a sample, X bar. We knew if we start with normal, X bar is also normal. So you do have to justify using chart A, and we were able to do that. We actually did it as we went. Number 12. I don't know if I've done number 12 yet. Oh, great. A radio station says 20% of phone-in listeners are male. So they added another male host and then recorded the gender of 200 phone-ins, viewing these 200 as an SRS from the population. Ew, that's not wise, because they had phone-ins, which isn't a true SRS. So go figure. All right. Assume that adding the co-host has no effect. So if P hat is the proportion of call-ins that are male, what are the mean and standard deviation of P hat? All right. To do the mean, we're fine. We can always do the mean. So the mean of, we're doing this mean and standard deviation of P hat. So the mean of P hat is the mean of the whole population, where they said, yeah, they said right here, the 20%, 0.2. So now we're going to go over to standard deviation of P hat, And we can only do that if n times p is going to be, I'm sorry, 10 times n is less than big N. So we're looking at that less than or equal to. So 10n, the viewing doing this 200 is 10 times 200. 10 times 200 is 2,000, so we assume that there's less than that number is less than the whole population of listeners. So we're going to go ahead and say okay. So we can do the standard deviation, which is the square root of p times 1 minus p over n. And I didn't do this one ahead of time, so without me tapping it out, p is 20%, and 1 minus p is 80%, and n is 200. So I guess I can do that. 0.2, 0.8 over 200, all under the radical. Dramatic pause while I tap that into my calculator. Whoa, I got a tiny whiny number. Let me try that again. 0.2 times 0.8. Enter. Okay, that looks better. Divided by 200. I guess it is tiny. Second, so now I'm going to take the square root of that, and I get, all right, 0.028, I'll say. All right, what assumption was made to find the standard deviation in part A? We already went over that. 10n is less than n. The assumption is there's more than 2,000 listeners. So 50 out of 200 callers were male. Does this provide sufficient evidence to suggest the proportion of male callers has increased from 20%? All right, so we're going to see what the probability of that is happening. So what's the probability that p hat is, does this probability sufficient evidence to suggest the males has increased from 20%? Well, let's just find out what is the probability of getting 50 out of 200 calls, or should we go more or less? Should we go the probability? First of all, we need a proportion, so 50 out of 200. We've got to put that in the calculator. And I got 0.25. So do we want to go p hat is greater than 0.25 or p hat is less than 0.25? So we want to know, does this provide sufficient evidence to suggest the proportion of male callers has increased from the 20%? So let's just find the probability that it's less than, and I'll think on that. And I also have an answer key, but not with me. So I'll verify that a little later. Probably I'll add a little addendum to this. So the probability that p hat is less than 0.25, we are going to change that to a z-score if we can use normal privileges. So we got to check, is np greater than or equal to 10, and n times 1 minus p greater than or equal to 10. So we're going to do that check. Our n up here was 20%, and our p was 200, so 0.2 times 200 is greater than 10 because it's 40, and 0.8 times 200 is greater than 10, so we'll check that off. So now I'm going to use normal privileges to find out the probability that p hat is less than 0.25. So I'm going to put 0.25 is my proportion of interest. I'm going to minus the mean, which was 0.2, divided by the standard deviation. Up here we got 0.028. And that is 1.78, 1.79 we'll say. And then I need a chart A. Guess what? I don't have one. I don't know how I didn't get this one done. So I will let you finish this one, and I will come back on after this video is over and give you a short update on this one. Go to chart A. You're going to find out what the percentage is. We do want less than 0.25. So if it's a high percentage of chance of that happening, then we would say that adding the male host probably didn't make a difference. If it was a low percent chance of that happening from chart A, we'll know. Then we would say that probably that it did make a difference. So I'll come back and add my thoughts to that when I have a minute to think about it. Let's end on this, and I'll come back with a little addendum to that. Here we have some textbooks, and the annual cost of textbooks is skewed left. This is not that population graph. But this data is for the population graph. So 50 random samples of side 32, so N, that's your N, are selected. And the IQR, remember that's Q3 minus Q1, for each is shown below. So we have an actual population distribution, sampling distribution of IQR. So they want to know, what's this dot right here represent? Well, all that is there was one of the samples, one sample, they took 50 random samples, so one sample of the 50 had an IQR, which is Q3 minus Q1, of 240, and that's all that means. Alright, so that's what happened on one sample. Is the sample IQR an unbiased estimator of the population IQR? Well, let's go up to the population data. I had the same thing below, but up here, what is the IQR for the whole population? This is the population data. We kind of have to calculate it. Q3 minus Q1. So we have 380, and Q1 is 215. So when I subtract those, I got a 165. So I want to know, is the mean of this pretty close to 165? So if I eyeball 165 on here, here's 160, and this is 170, 180, 170, 180, so 165 looks like it's about right there. Does that look like it's the mean of that distribution? It's a little hard to tell. We've got have to have like a balancing point there. Does it look like that distribution would balance if it was on a pin right there? So the answer is supposed to be yes, that does appear, and there's a little bit of judgment here because nowhere do we know what the mean of this distribution is. We could take forever and try to guess what that number stands for in that one, and this is 100, there's 3 of them, and put them all in our calculator and find the mean, but that wasn't their point. So they want us to see that this is slightly skewed, so this is probably where the mean is. So the mean is at the true parameter, so we do say it is unbiased. Is it an unbiased? Is a sample IQR an unbiased estimator? And the answer is yes, it is, because the mean of the sampling distribution is very close to the true parameter. Alright, so I'll come back and do a better job on number 12, and I'll talk to you about that in a bit. Alright, over and out. Carry on, class. Carry on.